In this video, we will do a quick review of quadratics, how to find a vertex, how to find the zeros, and most importantly, how to solve a quadratic inequality. We rely heavily on the zero product rule to solve polynomial functions. So when we're talking about a quadratic function, we're just talking about a polynomial of degree 2, but we separate them because quadratics have some formulas that we can use that make things a little bit easier. So we'll start here with quadratics. What should we know about quadratics already? What we should know is that the general form of a quadratic is ax squared plus bx plus c. And of course, we can have y equals. We could also have f of x equals. If it were a function, it is a function. But if we were talking about function notation. We know that the graph of a quadratic is a parabola and that parabolas are symmetric about the line of symmetry that goes through the vertex. So that means if we have some parabola and we have its vertex right here, that it's symmetric about this line here. We can find the vertex several different ways. We can use the formula x equals negative b over 2a, and then find the function value at that negative b over 2a. We can put the quadratic in vertex form, which is y equals a times x minus h squared plus k by completing the square, and then the vertex is just the hk that we have. Or we could use technology. We can also find the zeros or the x-intercept several ways. We can do factoring. We can take roots. We can complete the square. We could use the quadratic formula, or we can use technology. So we're going to look at some examples here, starting with finding the vertex, and we'll do it each one of the ways that I've listed there. So the first thing we're going to do is we have our quadratic here. F of x equals 2x squared minus 12x plus 19, and we want to use the vertex formula to find the vertex. So in that case, we're going to say x equals negative b over 2a. So a here is our 2 and b is the negative 12. So negative b over 2a would be 3. Then we want to find the function value at 3, which is 2. 3 squared is 9. 12 times 3 plus 19. That will give us 18 minus 36 plus 19. And that will give us 1. So our vertex here is 3, 1. So we're now going to use the same quadratic, and we will complete the square. So for this one, I am going to start by factoring a 2, but only out of the first 2 terms. I want to make sure that I have only an x squared. So I'll have an x squared minus 6x, and I'm going to leave a little bit of room here because I'm going to add something to both of these. All right, so what do I add? Well, when you complete the square, you take half of the middle term, which is negative 3 in this case, and we square it, and that gives us 9. So I'm going to put a 9 here. Now, that means that this now is a perfect square trinomial, and if you distribute this 2, what I've really done is added 18 to this side of the equation, so I must also subtract 18 to keep things even. So now I have 2. This perfect square trinomial factors as x minus 3 squared, and 19 minus 18 gives us 1. And so our hk is 3, 1. So again, we get the same result, which we should have by completing the square. We can also use technology to find our vertex. In order to do that, we put our function into y1, 2x squared minus 12x plus 19. It will sketch for us the graph, and then we will be able to find this by using the second function, calculate, and then go to, in this case, minimum. Sometimes it's a maximum. And we've done this before, but we look for the left bound, the right bound, and then we guess. So when we do our left bound, we're going to choose something to the left of what we believe it is. We'll choose something to the right of what we think it is, and then we will put it where we believe it is, and then hit enter, and it will tell us x equals 3 and y equals 1. That's how you find a maximum or a minimum, also called the vertex. Let's also look at finding the zeros of quadratics 3 different ways. So I have a new quadratic here. I have f of x equals 6x squared plus 7x plus 2. And when we're finding the zeros, also known as the x-intercepts, the fastest way is to factor. So we're going to start by factoring, and I'm going to use a method, I call it bottoms up. But we notice that because we have the 6 here, we need to factor a little bit differently. So we start by saying 6 times 2, that's the first times the last, and we list our factors of 12. So 1 times 12, 2 times 6, 3 times 4. And we're looking for 2 in that list that can give me a positive 7, which is positive 3 and positive 4. Now, at this point, you could stretch out that middle term and factor by grouping, but I like to use a method I call bottoms up. So I take my positive 3 and my positive 4, and I divide by my lead coefficient 6. So I'm going to take both of those and I'm going to divide by 6, and I'm going to get 1/2 and 2/3. Then I am going to put an x with those and bring those up, and I can tell that this function factors as 2x plus 1 and 3x plus 2. And you can FOIL that out to make sure that you get the same thing you started with. Now we use the zero product rule because we're looking for the zeros, and we set each one of these equal to 0. And that will give us x equals minus 1/2 and x equals minus 2/3. That's usually the fastest way to find the zeros of a quadratic. We might also want to take roots. Now, taking roots would probably not be the best way to find the zeros in this particular case, because it's not in a form where you could use it. But let me just show you. If I first put this into vertex form, so what I'm going to do here is I'm going to set this equal to 0. And I'm going to start, because I can't factor that 6 out like I did in the previous example, I'm actually going to divide everything by 6. That's going to give me 0 equals x squared plus 7/6 x plus 1/3. And similar to what we did before, we are going to move the constant over. We're leaving this space here. And we're going to add and subtract the same thing. Now, I take half of this middle term, which is 7/12. So let me put that over here, 7/12, and we're going to square it. So that's going to give us 49 1/44. Simplifying this, we're going to have 0 equals x now, factoring as we go. So when I factor this perfect square trinomial, I shouldn't have to really think very hard. This is going to be x plus 7/12. And I know that because that was the half of the middle term before I squared it. Then 1/3 minus 49 1/44 is minus 1 1/44. So that's the first part. You have to actually complete the square. So I probably would not use taking roots as a method unless it was already in this form. So at this point, I'm going to add the 1 1/44. And I'm going to take the square root of each side and get plus or minus, because we put the square root in, plus or minus 1/12 equals x plus 7/12. So I'll have x equals positive 1/12 minus 7/12, which ends up being minus 6/12 or minus 1/2. Or I get minus 1/12 minus 7/12, which is minus 8/12 or minus 2/3. So we get the same two results that we got from the factoring, but clearly the factoring was the faster and easier method. The next way to solve for the zeros of a quadratic is to use the quadratic formula, which is, let me just make a little line here, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, this would be x equals negative b. I'm going back to here to my original. Let me erase some of this. It's not going to let me. Darn it. Oh, there we go. Okay, so in this particular case, our b term is the 7. So negative 7 plus or minus the square root. B squared would be 49 minus 4 times a times c all over 2a. And I'll trust that you can simplify this, and you're going to also get negative 1/2 and negative 2/3. The last way to find the zeros is to use technology. And to do that, what we do is we graph it. Again, using our calculator, we plug it in for y1. 6x squared plus 7x plus 2. So if I use technology to graph this, I'm going to call this negative 1. So this will be negative 1/2. We're going to have negative 2/3 and negative 1/2, and just barely here. I only know that because I've already done the work above. But just like before, when we want to find like a zero, like right here, I go second function, calculate. This time we want to calculate a 0. And then we do the same thing, left bound, right bound, and guess. So we would choose a value to the left of where we thought the 0 was, to the right of where we thought the 0 was, and then we would guess. And we would just have to do that twice, once for each time that we wanted to find a 0. So finishing up with quadratics here, sometimes we know quadratic functions don't have real zeros, and in that case, it will not factor, and you have to use the quadratic formula or taking roots. So what would happen is you would get something that had a square root in it, but it had a negative number. So, you might have negative 7 plus or minus a square root of a negative, and we would say, that's not real. But we still could find the imaginary solutions. They just won't be called zeros because that's not where it crosses the axis. So the last thing for this video is quadratic inequalities. And if nothing else, I mean, the rest of this has probably been somewhat review, but quadratic inequalities are super, super, super important in your calculus class, which you will take next. So I want to make sure that you follow the process. There are other ways to do this, but follow this process and it will help you in calculus. So the process is make sure you have a 0 on one side of your inequality symbol. Second, factor the quadratic. Third, find the zeros of the quadratic as if it were an equal sign. And we call these, in calculus, we call these critical points. This critical point is going to separate your number line into different intervals. Then we're going to mark our critical points on the number line. We're going to use an open circle if it's just less than or greater than, and then we're going to use a closed circle if it's got the equal to. We're going to identify our intervals in interval notation, and then we're going to test any point in each interval and decide if it makes the equation positive or negative, and then we'll choose the ones that make the inequality true. So I have two examples here. The first one is already factored, so that makes things easy. We're going to assume that this is in fact equal to 0, and we'll find our critical points to be 1/3 and 2/5. So the next part of this is to put these numbers on a number line. So when I do that, 2/5 is 0.4, so that's going to be about here, and 1/3 would be before that. That's 0.3 repeating. And because this does not have an equal to, we're going to put open circles on these. So now I want to identify my intervals. Well, my intervals are in here, and they are -infinity up to 1/3, 1/3 up to 2/5, and 2/5 up to infinity. And what I like to do is make a chart. So I want to test some interval, and I want to know in the end if that's going to be positive or negative. So finding something in that first interval in here, I'm going to use 0. And I'm going to plug the 0 into this inequality. And that's going to give me, I think you can see if I plug the 0 in here, -1 times -2, and a negative times a negative would be positive. In the middle here, I'm going to choose 0.35 because that's between 0.3 repeating and 0.4. And what you're going to notice is when you plug that in, you're going to get 1.05 minus 1. So that would be a positive value for the first factor. And then you're going to get 1.75 minus 2, and that's going to be negative. So in this case, a positive times a negative is going to give you a negative. And then in this third interval, oops, I put that little that little parenthesis here in the wrong spot, did I not? Because it goes on forever. So I'll put it out here. So I'm going to choose 1, however, and that is going to give me 3 minus 1, which is 2, and 5 minus 2, which is 3, so 2 times 3 is going to be positive again. Okay, we're almost done. So what we do now is we look at the original inequality here, and we say we wanted things to be greater than 0, and that would be these two intervals. So our solution would be -infinity up to 1/3 union 2/5 to infinity. Let's do that again for this inequality here. So the first order of business is to factor. So if I do what I had done previously, 4 times negative 3 is negative 12. And you can see that the numbers that multiply to 12 and add to negative 11 are negative 12 and positive 1. I then am going to divide by that lead coefficient, which is 4. And I'm going to reduce. So the reduced forms here are negative 3 over 1 and 1 over 4. And so this inequality factors as x minus 3 and 4x plus 1, bringing those bottom numbers up. That means that my critical points are 3 and negative 1/4. Once I have my critical points, I put them on a number line. So here's 0, negative 1/4, and 3. Because this one has the equal to and the inequality, we're going to include those. And then we're going to write down our intervals. So this first interval is going to be negative infinity up to negative 1/4 bracket. We're also going to have bracket negative 1/4 up to 3. And we're going to have 3 up to infinity. And we're going to test values. Let's see what our test values should be. We'll make a little chart here as well. So what is our test value? Well, in this particular case, let's use negative 1. And if I plug in negative 1, I get negative 4 times negative 3. That will be positive. In this second interval from minus 1/4 to 3, let's test 0. That will give you negative 3 times 1, which is negative. And between 3 and infinity, let's test 4. So 4 minus 3 would give us 1. 16 plus 1 would give us 17. 1 times 17, positive. So if we want to know here where our solution set is, and we want it to be less than or equal to 0, our solution set is going to be negative 1/4 up to 3. That concludes this video on quadratics, and now we will move to polynomials in the next video.